Hello, everyone. So as Tom said, I'll be talking about the AdaptiveCpp standard parallelism implementation. And I'd like to start off with a question. So the question is, that kind of motivates all of this work: can heterogeneous computing be expressed directly within C++? And this is, of course, very closely related to a question that SYCL asks, which is, can heterogeneous computing be expressed with pure C++ syntax, but with an additional C++ API? So the modification is now that can we get rid of the additional C++ API that SYCL has and also just get by with what C++ already has? So basically, it's just a continuation of SYCL's line of thought. And indeed, the C++17 parallel STL already provides mechanisms to express data parallel computation. There are functions like std for each, std transform, transform reduce, fill, copy, and so on and so forth. And you could use them like shown here. So if you have some std vector with some that contains some data, then you could invoke a for each, pass in some policy that describes what kind of parallelization is allowed, and then pass in your code that would actually be invoked over all of the data elements. And this policy could be seek, which means that the algorithm must be executed sequentially, but it could also be par, which allows parallelization, or it could be par and seek, which allows both parallelization and vectorization. In that case, only explicitly vectorization safe code would be allowed. And of course, especially the par and seek policy would map very well to data parallel accelerators like GPUs. And if we already have such functionality in the C++ standard, then it is kind of attractive to consider just offloading calls to such data parallel C++ constructs, because that could potentially lower the barrier of entry into heterogeneous computing. It would also be highly idiomatic because you're just writing, regular C++. And perhaps we can even get a speed up for existing C++ programs that use this functionality simply by recompiling with an offloading aware C++ compiler. And this programming model is typically referred to as Stdpar, standard parallelism. And this programming model as an offloading model was notably pioneered by NVIDIA with their NVC++ compiler for their own hardware. But recently, other vendors have been making strides to also support this on their own hardware. For example, AMD has come forth with ROC Stdpar, and Intel has added the -fsycl PSTL offload flag to ICPX. In a similar time frame as both AMD and Intel, we in the AdaptiveCpp project have also started to work on this. And as you could guess from the title of the talk, also this is what this is all about, this talk. So typically an Stdpar implementation works in the way that you have some vendor programming model that is supported by some vendor compiler. And then the Stdpar compiler just uses a vendor-provided algorithm library implemented in that programming model to implement the C++ data parallel algorithms. For example, the NVC++ compiler calls into Thrust, which is written in CUDA. The ROC Stdpar compiler calls into ROC Thrust, which is written in HIP. And the ICPX compiler calls into 1DPL, which is kind of written in SYCL. Additionally, existing Stdpar compilers are mostly unaware of the Stdpar model, except insofar as they need to be to enable like the basic prerequisites. For example, to ensure that memory management works and that kernel outlining works without, for example, the CUDA device attributes. And once the code has been compiled, then existing Stdpar compilers generally just offload unconditionally. So our contributions are the AdaptiveCpp Stdpar compiler, which is basically the Stdpar support integrated directly into the AdaptiveCpp SYCL implementation. It is the first Stdpar implementation that is both open source and based on SYCL. It's also the first Stdpar implementation that can demonstrate performance across Intel, NVIDIA, and AMD hardware. I will show you the performance results later. It's also the first Stdpar implementation that attempts to diverge from this library-focused design and instead opts for a tighter integration between compiler and Stdpar model for performance and functionality benefits. So we introduce additional optimizations and features such as synchronization elision, automatic prefetching of data, and offloading heuristic, pointer validation, and so on. And because of that, we can demonstrate substantial performance improvements over the other compilers. So here you see an overview of the existing Stdpar compilers. So NVC++ mostly focuses on NVIDIA GPUs, it's closed source. ROC Stdpar only works on AMD GPUs, it's open source. ICPX focuses mostly on Intel hardware. and at least the compiler bit is closed source. Whereas AdaptiveCpp is not focused on one hardware vendor in particular. It works across CPUs, Intel GPUs, NVIDIA GPUs, AMD GPUs. You can even easily construct a binary that just runs on all of those. And it's open source and based on its own algorithm library, plus dedicated compiler features, plus dedicated runtime features for Stdpar. And the idea really is that you can start your application development in high-level standard C++, and then as you find performance bottlenecks in your code, perhaps then move those parts to SYCL, which would then give you more control and more optimization features to get more of it. So make your development cycle more productive. So how does it work? So on a high-level overview, basically we just provide custom algorithm execution and numeric headers, and then add new overloads for offload-capable algorithms for the par and seek policy. And the set of algorithms for which we support offloading is still smaller than for the other Stdpar compilers, but that is primarily because our goal was not on quantity, but to develop an innovative framework. And you can always add more algorithms later, because how to implement a parallel scan or so, that is mostly a known art. So that can always be done later. If you're calling an algorithm for which offloading is not yet implemented, then it will work and compile and run, but it will run on the host. And you can just enable it using the new flag --acpp Stdpar. A very important problem with Stdpar is memory management, because C++ has a flat memory hierarchy and is completely unaware that in your system there might be multiple distinct memory spaces, such as a separate host memory and a separate device memory. So therefore, if you want to support offloading in pure C++, the memory needs to be available on the device without the user calling any special memory allocation functions or explicit data transfers. And also, to make things more complicated, the compiler also cannot really help you, because the compiler and runtime in general cannot determine all allocations that might be used on device. For example, there might be indirect access, which refers to the case where additional pointers are loaded from memory, which could happen, for example, if you have some pointer-based data structure, such as a linked list or a tree, or if the pointers are somehow obscured to the compiler, if they're passed as an integer or so to the kernel and then cast back to a pointer inside your device code. So one obvious solution here is SYCL 2020 Unified Shared Memory, USM. And in particular, there are two types of USM that could be helpful here. The first one is SYCL System USM, which refers to the case where all of the host memory addresses are directly accessible on device. And that could, for example, happen if the host and device are tightly integrated, perhaps they share the same physical memory, or if the device is the host CPU itself, or if technology like Linux HMM is involved. In that case, basically we're done, so problem solved, great. The problem is only that this, at least for now, is only rarely available in practice. The other alternative is the SYCL shared USM model, where memory automatically migrates between host and device as needed. And this is typically implemented with the hardware emitting page faults and then the driver handling those page faults by then migrating memory pages. In that case, we don't need explicit data transfers, but we still need special memory allocation and deallocation calls. So we need to call SYCL malloc shared or SYCL free in SYCL. And this is more widely available and this kind of works on Intel, NVIDIA, and AMD GPUs. So for generality, at least for now, an Stdpar implementation cannot assume that system USM is available, and therefore, in the following, we assume shared USM. If you want to support Stdpar through a shared USM model, then you need some kind of memory management interposition layer. So basically, you want to intercept all allocation and deallocation function calls, operation new, operator delete, malloc, free, realloc, and so on and so forth, and reroute those through shared USM. And this is how all Stdpar implementations currently work. Of course, there's like one major caveat, which is what happens if you actually pass in a stack pointer then to your kernel, because this obviously only works with heap allocations. And I will touch on that later. In AdaptiveCpp, we handle this by replacing allocations locally with a compiler pass that basically replaces your allocation calls to a call to shared USM allocation. And deallocation is handled globally by just intercepting the symbols. And that allows us to, in the entirety of your program, be able to support both deallocating regular memory as well as USM memory. So you can have memory ownership transfers between different program components. In practice, this is extremely tricky to get right, and it's very, very technical and very challenging. The paper goes into more detail as to how exactly this is done. So I will only give you some examples and some example solutions how we do it. So for example, you might run into some infinite recursion problems, because in the process of allocating shared memory, the SYCL runtime itself might also do some allocations. So then you have a potential recursion. There can also be a negative impact on submission latency, because in the submission path of the SYCL implementation, there might also be some allocations or deallocations. You can run into ODR issues, and there could be memory allocation or deallocation requests when the SYCL runtime is not available, for example, very early in program startup or very late at program shutdown. And so things that AdaptiveCpp does is there's detection for recursing. There is a dedicated allocation tracking data structure that we can use to avoid having to call into the SYCL runtime too often. There is also extra logic to disable allocation interposition inside the SYCL headers so that the SYCL submission path remains fast. There is also full call graph duplication for both the interpose and non-interpose allocation cases and insertion of ABI tags so that we can avoid ODR issues and distinguish intercepted symbols. Talking about the execution model, C++ does not provide any information on the target device in its API, so we have no idea what to run on. So therefore, all Stdpar implementations are generally challenged when you want to use multiple devices. And that is the same with AdaptiveCpp. So what we do is we just use the SYCL default device, and there are environment variables that you can set to influence which device this boils down to. Then we dispatch to thread local in-order SYCL queues, and that allows you to still express concurrency within one device by just submitting your Stdpar work from multiple C++ threads. Another problem is that C++ Stdpar model generally requires waiting after every single kernel submission, because the assumption is in C++ that once an Stdpar algorithm returns, the changes that it has made to the memory are visible to other code immediately. We, however, have an extra optimization that can detect and elide unnecessary synchronization. I will discuss this more later. Now, obviously, if you want to seamlessly integrate into C++, then in principle, all the features that are allowed in C++ in the Parallel and SYCL algorithms should also just work in your offloaded scenario. But this often is in conflict with device code limitations, which for SYCL include that kernel lambdas must capture by value, never by reference, that host pointers may not be dereferenced, that function pointers or virtual functions are not allowed, that exceptions are not allowed, that non-trivial types used inside kernels require specializing the SYCL is device copyable type trait, that built-in functions must be from the SYCL namespace and not from the SED namespace, among other things. So how would you address that? So basically you can have two different strategies. So firstly, you could try to just add extensions to support these features in your SYCL implementation. Or you can also detect whether unsupported functionality is used, and if so, just not offload. And that might, however, require different logic for how you handle your diagnostics in your SYCL compiler, so that you don't emit an error immediately. Currently, as far as I'm aware, no Stdpar implementation currently solves all of these issues. However, what we do is we try to address and mitigate the most common issues that we ran into. So therefore, we can handle some cases that some of the other implementations cannot handle. So for example, we support SED math built-ins in device code, and this is handled by a new LLVM pass that just remaps libc math built-ins to our own built-ins. And rock Stdpar, for example, only supports this partially. We also support capture by reference, and this works because we validate all the kernel pointer arguments that the compiler sees when the kernel is invoked. And if a host pointer is invoked, if a host pointer is used, then the algorithm is just not offloaded. ICPX, on the other hand, just refuses to compile whenever a capture by reference is used, even if the reference points to a valid USM allocation. AdaptiveCpp also supports non-trivial data structures, whereas ICPX just doesn't allow this unless you use this SYCL is device copyable type trait, which is completely in line with the SYCL specification, but it's too restrictive for Stdpar. AdaptiveCpp also supports memory ownership transfer between different program components, and that could easily happen, for example, if you have some library that uses STD shared pointer and your application uses STD shared pointer and you're passing things between. And ROC Stdpar, for example, would just crash in that case because it only intercepts deallocation locally and cannot handle when things move to a different program component. Now, we've also put in a number of specific optimizations for Stdpar. Stdpar has a simpler execution model than SYCL. Everything is just in order. Events are never used. So very, very simple. We don't have any DAG construction. Therefore, we can bypass some unneeded SYCL layers. And therefore, the Stdpar model generally in our compiler has lower submission latency than SYCL. Also, USM allocation and deallocation is generally more expensive than regular allocation or free. So what we've done is we've introduced a USM memory pool and we just serve out allocation from that memory pool. We can also automatically emit calls to queue prefetch for the allocations that we detect that are used inside kernels. And this can be useful because it can make the driver emit a single data transfer, which might be more efficient than having every page fault individually and be then migrated individually. We support different prefetch modes. So if the prefetch mode is always, then a prefetch will always be emitted. If it's never, then the optimization is disabled. If it's first, which is the default setting, then the prefetch is only emitted for the first time an allocation is used on device. And if it's set to after sync, then a prefetch is only emitted the first time it's used after a barrier. Another important optimization that I've mentioned already is synchronization elision. So if we have a code in the above, then until the results are actually accessed on the host, the fact that we have to wait after every Stdpar call is just unnecessary because it's not even observable, right? So we could, in principle, just elide synchronization after each of these Stdpar calls and just wait before we access the results on the host. And this is very important because synchronization can be very expensive. And we can detect these cases and elide synchronization in the case. And how exactly it works, I refer you to the paper. This only works within one translation unit at the moment. So if you call some functions that are defined externally, this currently prevents synchronization elision. But I think this could be addressed by moving this optimization to the link time optimization pipeline in the future. It also doesn't work for algorithms that need to directly return the results. For example, if you call transform reduce, that directly needs to return the value of the reduction that was calculated as a result. So in that case, you cannot run it asynchronously, of course. We've also put in an offloading heuristic because offloading is not always beneficial. If you have a very small problem, then the latency of offloading can mean that it's actually faster to just run the algorithm on the host. So what we do is at runtime, we record the execution chain of the operations and try to predict the next ones. And then we predict how long a certain number of operations in both the offloaded and non-offloaded case would probably take. And to this end, we maintain a database where previous kernel runtimes are stored both for offloaded and non-offloaded cases. But you need to first make basically a host performance run to calibrate the results for the host so that we know whether we are faster or slower when offloading. And we also take into account estimates for the data transfer costs between host and device by looking at how large the allocations are used that are used inside the kernel. And this, I'm not claiming that this heuristic is perfect. This is like a huge research topic in itself to come up with such heuristics. I'm just saying that it worked well for our use cases. And the point is, offloading heuristics can be important. The point is not that this is the best heuristic ever. So here you see a comparison of different optimizations. So the memory pool is like a common optimization that I think most Stdpar implementations implement, but the other optimizations, as far as I know, are new. So now to the evaluation part. The paper discusses more in detail how exactly things were run and compiled. So the important point is that we've been looking at some CPU hardware. We've been looking at AMD MI100 GPUs. We've been looking at NVIDIA A100 GPUs, as well as the Intel Max 1550 PVZ GPUs. And before we discuss the results, we first need to quickly touch on AMD GPUs and XNAC. to understand the results. So AMD GPUs depend on a hardware feature called XNAC for shared USM. And XNAC is important for instruction retry in case a page fault happens. Without XNAC enabled, the ROCm stack just maps shared USM to device accessible host memory. In this case, in principle, every memory access needs to traverse PCI Express, which is going to be very, very, very slow. The problem, though, is that XNAC is a fairly elusive feature because most consumer GPUs lack XNAC support on the hardware level entirely. It's also not enabled on most HPC systems, and you also cannot enable it as an unprivileged user because you need special non-standard Linux kernel arguments. So we were lucky because our system supports XNAC, but in practice, most systems currently do not support XNAC. So therefore, the performance without XNAC is actually more practically relevant than the XNAC-enabled performance. Now, the first question we want to investigate is what is the impact of having all the memory be managed automatically through the shared USM interposition layer. And to this end, it's useful to look at a memory benchmark like Babelstream. So we noticed that on AMD, the XNAC results failed to validate. So therefore, we only show the non-XNAC results for this benchmark. And also the ICPX compiled benchmark just crashed inside internal SYCL header code. I think there was a problem with the memory management interposition there. So as a workaround, to still get some results on ICPX for Babelstream, we present results where the Babelstream benchmark just directly calls into DPL and explicitly calls malloc shared. This is a simpler problem than full memory management interposition, so it's not 100% comparable, but gives you some baseline. So here you see the results. So first on the CPU device, we see that actually AdaptiveCpp with Stdpar outperforms the SYCL version of the benchmark with AdaptiveCpp. And that is primarily because of the lower submission latency of the Stdpar version, because the SYCL version would have needed a larger problem size to saturate performance there. On the NVIDIA GPU, we see that all the compilers, and both with Stdpar and SYCL, perform well with shared USM. And on the AMD GPU, we find that ROC Stdpar really needs XNAC, and it's not competitive without, whereas AdaptiveCpp actually does not depend on XNAC. And the reason for this is because of our automatic prefetching optimization. Turns out that you can still, even if you don't have XNAC, get a shared USM allocation to become device resident in ROCm if you prefetch it before you use it and it's suitably aligned. And this is exactly what happens here. So in summary, we can say that Stdpar shared USM can be fairly efficient, and there's not an inherent problem with that. Next, I've looked into some more complex mini apps. So I've looked into MiniBute, which is a compute-bound molecular docking mini app, as well as the Cloverleaf and Tleaf mini apps. And now the question is, how do Stdpar compilers perform compared to native vendor models? And that would be NVCC compiled CUDA on NVIDIA, HIPCC compiled HIP on AMD, and ICPX compiled SYCL on Intel. I've tested all of the AdaptiveCpp prefetch modes. The best were always first or never. So I'm showing results with these two prefetch modes. And here you can see the performance normalized to the native model. And I've highlighted the fastest results for each benchmark on each hardware. And what I found across the board is that AdaptiveCpp outperforms the vendor Stdpar models for 2 out of 3 apps on all of the systems, and sometimes even by an order of magnitude, such as, for example, in the AMD GPU case without XNAC, but also in the ICPX case where there appear to be some serious performance issues for the more memory-intensive Cloverleaf and Tleaf applications. And I believe that there is some problem in the memory management interposition layer. In any case, AdaptiveCpp was always faster than the host PSTL, so you always get a speed up, which is good, and that was not the case for all of the vendor compilers. Lastly, I've been looking at Lulesh, which is a shock hydrodynamics mini app. And this is actually a fairly challenging problem for Stdpar compilers because it does lots of allocations and deallocations inside the hot computational path. And it also does lots of indirect memory access. And it's also highly latency sensitive. So it's very sensitive to the fact that Stdpar in principle has to wait after every kernel. And here you see the performance on the left side of the Stdpar code normalized by host Parallel-STL, on the right, normalized to the NVC+, the AdaptiveCpp Stdpar performance normalized to the NVC++ performance on A100. And I've shown results for both the optimizations that we've put in enabled and disabled. And if we look at the case where everything is disabled, which would be this case here with the black triangles, we find that it's not performing that well. It only scales to around 2x of host PSTL performance. But then if we enable the memory pool, performance jumps to this line roughly. So then really performance starts to improve. And that really shows that memory pool is a crucial base optimization that you need to have in your Stdpar implementation. Now, if you also enable synchronization elision, then we are on this line. So then we really get some immense performance boost. And looking at the other plot, we find that in this case, we outperform NVC++ by up to 80% on this hardware. If we now also enable the automatic prefetching, in this case, it was detrimental for performance, so then performance goes down again. And this is because of all of the indirect access that Lulesh does. So the compiler does not actually see even the allocations that are particularly relevant for this problem because they're all accessed indirectly, so it's not even prefetching the right thing, so it's just introducing additional latency. On AMD, I found that the ROCm stack was severely challenged with this problem. If you enabled any of the automatic prefetching, then the driver stack would just crash. And if XNAC is enabled, then performance was even worse. So here you see the ROC Stdpar performance. And if you enable XNAC, then it drops by multiple orders of magnitude. So it's even worse in that case. The same is in principle also true for AdaptiveCpp. However, our offloading heuristic detected that this was not running efficiently and therefore just decided to not offload the code. So that's why the AdaptiveCpp results here are around 1.x, because you basically get the same performance as just running on the host PSTL, because it detects that in this case, it's better to not offload. So conclusion is that offloading heuristic is important. So what happened on Intel? So ICPX just doesn't compile Lulesh because it does capture by reference. With AdaptiveCpp, it compiles, but it hangs inside the Intel driver somewhere. I'm not sure what's going on. I only had 2.5 days, so I didn't have on the system, so I didn't have a lot of time to debug it. But I could verify that it runs fine on Intel iGPUs, even though the results on this on the iGPUs were not particularly exciting because it was also slower than the host PSTL. So the offloading heuristic just decided to not offload it. So in conclusion, the integration of heterogeneous computing directly into C++ is possible, but if you want the best results, then you really need to opt for a deeper integration of the Stdpar model into your compiler and runtime. AdaptiveCpp is the first Stdpar implementation to attempt this with new optimizations like synchronization elision, automatic prefetch, direct calls, so lower-level runtime functionality, and so on. We outperform the vendor solutions for a majority of the tested applications, and we outperform NVC++ by 80% on A100 with Lulesh due to synchronization elision. Unlike ROC Stdpar, we also can work on systems efficiently that don't have XNAC enabled, which is probably going to be the common case. And we also, the AdaptiveCpp implementation also did not exhibit any of the performance weaknesses that either ROC Stdpar or ICPX exhibited. Also, I want to point out that after the paper submission, we made some additional compiler improvements that were not specific to Stdpar, just general compiler improvements. And I expect that kernels would be even faster now. So if you rerun the benchmarks now, performance would be even better. All right, that's it. Thank you.
Hey, great presentation and great stuff. Question, you said you support copying things without specializing device copyable.
Yeah.
So how does it know, like, if there's like a copying instructor, like where it would run that, or does it just see that that's trivial and just mem copy it?
I think it's just more permissive. I think there's if you have a class that really does some non-trivial stuff in its copy constructor, then I think in many cases you might already violate the vectorization safe assumptions that Par and SYCL has. But I think there are also cases where the code is just not particularly well written. So you have some copy constructor that is like user provided, but actually does something fairly trivial things. So really it doesn't matter that much. And I think this is what we've been seeing. And this we can support. And that makes sense to support.
Cool, thanks.
You mentioned that one of the limitations is you cannot specify the device, so you're just defaulting to the default device.
Yeah.
Do you have a recommendation on standard improvement to enable the ability to help specify the device?
I mean, obviously, it's very simple. I mean, this is a very complicated question because the C++ standard is completely unaware that there might be multiple devices in the system. So if you want to have some explicit control over that, then ultimately you'd have to have some device query API inside C++ or something like that. And I don't think this is ever going to happen. So Nevin's already shaking his head. So one thing to work around that could perhaps be to express devices with affinity domain things or something like that and make it more implicit. But I don't know. I don't think we are at that level with C++ yet. Nevin wants to respond to that.
Yeah, I mean, proposals welcome, but more seriously, I mean, C++ doesn't really know much besides, there's one process with multiple threads and multiple cores on a homogeneous CPU kind of thing. Or compute rate device. It doesn't know more than that, and it would quite literally take the committee, 10 to 20, probably 20 years to make it happen, right? Because the committee wants things that'll last a long time and go across a whole wide variety of architectures. And what's the general thing? We explore that in SYCL, and we don't know what the really general solutions are to that a majority of vendors would let be put into the standard.
I think the sender receivers API is very interesting. I don't think it can quite compete with like this old school regular parallel STL in terms of simplicity and idiomatic express. I mean, it's so simple to just say STD for each, STD transform, reduce, that I think it's going to be accessible to far larger potential user base than having to work with complicated sender receiver type programming. But I think if you really want the control, then I think you'll have to end up with something like senders receivers.
Hi, I wanted to ask, so you can do the stuff with like parallel arguments like SD transform, SD for X, etc. Like, what about like SD ranges? Like, you can do like something fancy also with that, just like the C++20 interface with all the view, etc.
I mean, with ranges, the same thing applies to our offloading solution as with like the interaction with regular host PSTL and ranges. So there's no magic going on there. If you can express some kind of range and you can run parallel STL calls on it, it will just work.
Thanks.
Yeah. I was just wondering if your heuristic kind of takes into account where the memory, or at least you think the memory is currently located.
Yes, because we know that we are currently offloading, and we know that the memory has been used on that device already, for example, and then we can basically estimate the data transfer cost.
So do you think some additional layer would always sort of be needed? I mean, I'm thinking of like, architecture specific things like memory hierarchies, like shared local memory and these kinds of things to have be able to write, very performant sort of code.
I think it depends. I mean, if all you want is like a reduction or so, then you can just call the parallel STL algorithms for reduction, and they will ideally have internally optimized code paths for different hardware. If you really want to have like your own data parallel for each kernel and want to put in your own optimized local memory usage or so, that's currently not possible with C++. In that case, that would be one case where I would say that SYCL could come in. So in that case, if you want to optimize further, I would say, well, then just write your kernel in SYCL where you can express all of these things. And you can mix and match those, right, in the same application.